Alright, I'm going to try doing this thing as my intro where I start off of the out of the shot and then go in so that there's a few seconds in the beginning where you can actually see what's on the board without me being in the way. That might be a little useful. So anyways, we're talking about representations, and so we talked about intertwining maps. So intertwining maps are functions in the set of linear maps from vector spaces v1 into v2, such that for every single g we have this going f composed with row 1g is going to equal row 2g composed with f. And so if you let hom g v1 v2 be the vector subspace of hom c v1 v2, so and this is going to be the set of G intertwining maps. So the difference between this is if you see the C there, then that's just going to be all linear maps. If you see the G here, then that means that they're linear maps which are also G intertwining. And why is that a vector subspace? Well, if you look at this condition here, if you had, you need closure under addition and scalar multiplication. For scalar multiplication, if you've got like f in here and you just threw a lambda next to that f, clearly the two things would still be equal. If you had f plus g here and f plus g here, then they'd be equal because f plus g composed with row 1. G is not a good thing to say here because g could easily be confused with this group element g. So let's say f1 and f2. So if you have f1 plus f2, then f1 plus f2 composed with row 1 of g, you can distribute it. And so it's going to be f1 composed with row 1g plus f2 composed with row 1g. And that is because these things work nicely. Yeah, because composition of functions. So it all works out nicely, and you can distribute the composition of functions through the addition, and then each of the separate terms will be equal because of the fact that row 1 and row 2 are representations. No, they'll each be equal because you'll be applying the fact that f1 is G intertwining and that f2 is G intertwining. But anyways, it'll all work out. So if there's any confusion on that, just work through it yourself and it will be fine. So anyways, we have a lemma. If we've got f that's in hom g of v1, v2, then certainly kernel of f is going to be a subspace of v1, and the image of f is going to be a subspace of v2. If those aren't completely obvious, that's fine, but you should work through those. And these are subrepresentations. And I guess another interesting thing to note here is that there's sort of interesting levels of things that you think are easy enough that the person you're teaching should do on their own. Because I know, for example, this whole lemma was something that my professor thought that we should just do it our own because it was easy enough. And I mean, it is fairly easy, but there's still it takes a couple lines here. And so similarly, the kernel of f being a subspace of v1 and image of f being a subspace of v2, that's another thing that he sort of said was just kind of obvious, and I agree with that. That's, at least to me, it's a little easier. But just because it's not completely immediately obvious to you isn't necessarily a bad thing. If anything, it tells you more about the style of the lecture than about the material itself. Although you'll sort of start to get a feel of different lecturers and different presenters have different thresholds of what they think is easy enough that the person they're lecturing to should do it, and tricky enough that they'll present it. So anyways, I'm going to go through and present this, and part of it was because I wanted to actually write this out on my own. So anyways, the first thing we want to prove, okay, so to prove that the kernel of F is a subrepresentation, we want to prove that it's G stable. So we want to take some element V of the kernel of F. Oh, I'm actually noticing something here. There was something that I had to fix in this actually, so this is not a completely yeah, this is not a complete, I made some errors in this, particularly because we know that F is a linear map, but we can't necessarily do this. And so hopefully I don't need to redo anything. So, but let's see if I do. Rho G of F of V is equal to rho of... No. In fact, we can just completely erase this. Sorry, I'm getting my head ahead of myself. I just noticed that and wanted to fix that before I continued. Anyways, okay, so back to what I was doing before. So we want the kernel of F to be G stable, and so what we do is we use this fact. And so you take an element rho 1 of G of V, and in order to have G stability, you want to prove that this is an element of the kernel. And so you want to prove that F evaluated at this element is 0. But luckily for us, F evaluated at this element can be written this way by the definition of a G intertwining map. And so F composed with this is equal to rho 2 of G composed with F, also evaluated at V. But V is in the kernel, so F of V is 0. So this is just rho 2 of G evaluated at 0. But rho 2 is it's a bijection on it's a linear bijection on V2, and so it sends 0 to 0. And so this evaluates 0, and so F evaluated at rho 1 GV is going to be 0, which means that rho 1 GV is in the kernel. And this confirms that the kernel is G stable, and so restricting rho 1 to the kernel gives us a subrepresentation of V1. Typically, after you had that the kernel of F is stable, you could just say that kernel of F is a subrepresentation. But at least for now that we're still a little early on, I like including this the map that's associated with it. Okay, so we have this. Now suppose we have an element of the image of F. So obviously any element of the image can be written as F of V for some V in capital V. Okay, so then for every single G, we want to prove that rho 2G of FV is also in the image, because that will prove that it's stable under G. But we can write rho 2 of G of F of V. This is exactly rho 2 of G composed with F, and then evaluated at G. But this whole thing is equal to this. So this evaluated at V is equal to F composed with rho 1 of G evaluated at V. So this is equal to the image under F of some thing here. We don't really care what it is. All we care about is that it's a vector. So that's all. As long as this is just F evaluated at something, that means it has to be in the image. Okay, so it's in the image, and so the image is G stable. And so restricting rho 2 to the image will give us a subrepresentation of V2. Okay, so that's that. Okay, now for the next thing. So let's look at an example. So we're going to take our group G to be Sn, which we know acts on the set of indices from 1 to n. And now we're going to let V be the collection of all complex valued functions from x into c. So you plug in an index between 1 and n, and you'll get out a function in c, or a complex valued number. But it turns out that this collection of functions is isomorphic to Cn. And to see that, you want to look at a basis. And we have this basis ei from 1 to n, where ei evaluated at j is delta ij. So ei is going to be 0 at every index between 1 to n except for I. And at I, it's going to equal 1. And let's see here. Certainly the span of this is certainly this will span the space of functions from x into c, because any function from x into c is determined, like you plug in an index and it gives you a scalar some complex number. And so what you can do is you can just take a whole bunch of these EIs, like for each EI you multiply it by whatever our function evaluated at I is. And then you add all those together, and then you'll get that function back. And so any function is a linear combination of these things. And I guess you have to do a little more work to prove that actually is a basis, but I'll leave that to you if you're so inclined to prove that. I'm fine just leaving it at this. Anyways, so we've discussed how to put representations on things like this, where we have a group acting on a set, and we have a vector space of functions on that set. So functions from that set into C, and we let that action is given by, if you have here sigma is in G. Oh yeah, at first I'm like, why did we decide to go with sigma? But it's because we're in Sn, and sigma is a common notation for elements of Sn. So rho sigma ei at j, remember this is how we define this in general for general group actions, where tau is the automorphism from G into that set. No, tau is the group homomorphism from G into the set of automorphisms on X. But anyway, so it's, you take EI, you take this thing, and then you evaluate it at tau of sigma inverse, the sigma coming from here, that evaluated at j. And now let's actually just figure out what it is. So this thing, tau of sigma inverse, well, here the group action is just left multiplication. And so tau of sigma inverse evaluated at j is just evaluating sigma inverse at j, i.e. taking the permutation sigma inverse and seeing where it maps j to. Okay, so this is ei evaluated at some index, and by this formula it's just delta of I comma and then whatever index this happens to be. Okay, so this is going to be 1 precisely when I equals sigma inverse j. Multiplying that equation on the left by sigma, you get it's 1 precisely when sigma I equals j. But then using this formula again, you can write this as E sub sigma ij. And so rho sigma eij is going to equal E sigma ij for every single index j, which means that rho sigma ei is just E sub sigma I. Okay, so that's how we define that's how this this representation is defined on basis elements, and you just extend it linearly to the whole vector space. And you can do that in general. That's something that we do a lot with representation theory. You have a function and you define it on a basis, and once it's defined on a basis, you can extend it linearly. Okay, so, but now let's look at subspaces. So here's a subspace that's not too difficult to find. So if you take the element lambda, some element in the span of the... Ooh. No, this is not quite right. It's not the span of these... well, it's definitely not right, because it's not the span of these basis elements, because the span of the basis elements is going to be the whole vector space. It's the span of precisely the element sum 1 through n of ei. So e1 plus e2 plus e3 all the way up to en. That is an element, that is a vector in V. And so this is just a constant multiple, or just some scalar value times this vector. And let's see what happens when we evaluate rho sigma at this vector. Okay, so rho sigma of this vector, you use linearity and linearity of rho sigma, and you can just pull that lambda and that sum outside, and you get these rho sigma ei's on the inside. But we know what rho sigma ei is. It's rho sigma ei is e sigma I. So we just plug in e sigma i's here. But here, what we're doing is we're taking all of these ei's and we're permuting them via sigma. But we know that this permutation is a set bijection. And so you're not really changing anything here. You're just permuting the order in which you add things. And since this is a finite sum and everything works nicely, it doesn't matter what order you add them in, because addition is commutative. And so you could just, this sum is going to be the same as this sum. And so rho sigma of this is precisely this. And so in fact, what this tells us is that the span of this element is G stable. And so it yields a one-dimensional subrepresentation. And of course the reason it's one-dimensional is because it's just the span of a single vector. And so it's going to have dimension 1, and you just take your representation, this one, and you restrict to this subspace, and it gives you a one-dimensional representation. Okay, so I'm sorry about all the issues I had on the board initially, but yeah, that's a good, more of an introduction to representation theory, and we'll go from there.